everyone, it's Mrs. Griffin with the Unit 8 Lesson 7 video. We're going to talk more about proofs that use circles. So our first example here doesn't have a picture, and it's not very clear even what the givens are. There's no letters, so we do need to draw a picture for ourselves. So we're going to start by drawing a circle, and we're going to give it a center point. I'm going to call it point O. And I need to prove that if the center, O here, is equidistant from two chords, then the two chords are congruent. So this is my proof. Anytime it's an if then, the then is the proof. And our given means we have to figure out how we would show this. So for starters, if we're trying to talk about two chords that are equidistant from the middle, when we measure how far away chords are or segments are from anything, I always measure in a perpendicular way. So this chord and this chord are an equal distance apart, and I'd be measuring perpendicular. And what I would end up saying is the distance between each chord and the center is going to be congruent. So if I give some letters to all that, I'll call one of the chords PQ, I'll call the other XY, and then where they meet, I'll call A and B. Okay, so basically what I'm trying to show is that if I have OA perpendicular to PQ and OB perpendicular to XY, that OA and OB are congruent to one another. And if that's true, then PQ and XY should be able to be proven congruent. All right, now I don't have any triangles here, so I'm going to give myself a couple of triangles to work with. Remember that I'm going to add in radii, because that's really the only thing I should be adding to a picture most of the time. So OQ I'll add in as one radius, and OX I'll add in as the other. Alright, and by adding those in, I've now created a triangle here and a triangle here. Okay, now because of the perpendicular lines, when I measure perpendicularly, I'm going to end up having two congruent angles. So I'm going to call them angle 1 and angle 2. And if I was doing proof blocks, it would look like that. Okay, another thing to keep in mind is that those two radii I just drew in there are congruent because all radii of a circle are congruent. And so that is coming from the given of circle O, which I really should add into both parts, that all radii of a circle are congruent. So OQ and OX that I just threw in there have to be congruent to one another. Now if you look at my pictures, I have the OA and OB from the given. Now I have my right angles and I have OQ and OX. I have ASS, but remember that if it's ASS, I can really change it into HL with right triangles. So what I'll do is I'll add in that step that right triangles have right angles in order to show that triangle OAQ and OBX are right triangles. And what that allows me to do is say, okay, it's not really ASS, which is not allowed, but HL instead. And so my triangles will be congruent by HL. Remember, the only thing that can follow one of those would be CPCTC. And so after my triangles are congruent, I have to figure out which parts are going to help me prove this. Now those segments, PQ and XY, are too long for my triangles. I can only get about AQ and XB being congruent. Now I could do a whole nother triangle proof and do more there, or I can realize something else is true. When I drew OA in and I said it had to be perpendicular, because it's from the center, it's just like a radius in some of its properties. So those two radii there can follow the same rule, that if you have a radius that is perpendicular to a chord, it's going to bisect that chord. Okay, so a radius perpendicular to a chord bisects. It means that OA will bisect PQ and OB will bisect XY because they're coming from the center. They behave just like radii. And so I can put that same thing here. Now we're going to use something a little bit tricky here. Instead of using the bisector to talk about the other pieces, I'm going to do something a little bit different. I'm going to say that means that because QP is bisected, it's cut in half. And therefore, AQ is half of PQ, and XB from CPCTC is half of XY because of the definition of segment bisector. And we've done that, just not many, many times. So again, the one from the CPCTC AQ is half of the whole chord PQ, and the other one from the CPCTC XB is half of the chord XY. And then because halves of congruent segments are congruent, that would mean that the whole chord PQ and XY has to be congruent as well. So a little bit tricky here. All right, on to number 2, less tricky. So we have very straightforward givens. We're going to throw them in. AC is a diameter. It's circle F. And AC is perpendicular to AB. Okay, now we're trying to prove arc AD is congruent to arc AB. This is one of the theorems that we've used, but remember, you can't use a theorem to prove itself. You're showing why it's true. So one thing that we know is that when we have a diameter perpendicular to a chord, it bisects the chord. That just happened in our previous proof. And so if the diameter is perpendicular to the chord and bisecting it, that means that the diameter AC bisects chord DB. And then we know what a segment bisector does. It divides a segment into 2 congruent segments. So we would be able to say that DE is congruent to EB. Keep in mind also that these are perpendicular. So we can do the fact that perpendicular lines form congruent right angles also and get our angle 1 and 2 to be equal to each other and equal to 90. And then we also, for these 2 triangles, AED and AEB, can use reflexive. And that would be segment AE for both triangles is congruent to the other side. And now I have a triangle proof. So I can use this side angle side to say that triangle DAE is congruent to triangle BAE. Okay, and then the only thing that can come after that is CPCTC. And so CPCTC is only to prove sides and angles of those triangles are congruent. Since we're trying to prove arcs, we're not done with that point. So we have to pick the thing for CPCTC that will help us get to arc AD and arc AB. So what we're going to pick is the chords that cut them. So we're going to say that segment AD is congruent to segment AB by CPCTC. And then since congruent chords cut congruent arcs, if these segments are congruent, the chords have to be congruent as well. So we're going beyond CPCTC with a circle rule. Once we get the segments, we can use them to get the arcs. Okay. Now, number 3 does have triangles in it, but there's an easier way to do this one, because if you notice there's no letter here, we could put one there, but it's a clue to us we probably shouldn't need it. So let's look at what we were told. We were told arc BC and arc DE are congruent, and we are trying to show segment BE is congruent to segment DC. Thinking about what we had in the previous one, in order to prove the segments are congruent, one of the things we could do is show that this pink arc is congruent to this blue arc, because the congruent chords cut congruent arcs. So I'm working backwards in my thought here. If I can get those bigger arcs congruent, then the segments would have to be. Notice that they overlap. Arc CE is reflexive. So what I can do is say that arc CE is reflexive, and then I can add it on to the 2 they gave me. I can take BC from my given and add on CE. I can take DE from my given and add on CE, and I would get larger arcs that way. So I'll take my arc BC congruent to arc ED, and the fact that I can use reflexive with arc CE, to create an addition problem. And remember, when you do addition, you're adding your left pieces and your right pieces together to make one long addition sentence. That BC plus CE would be congruent to ED plus CE, because equal things added to equal things have equal results. After that is always substitution, so I would be able to then put them together. When I take BC and CE and put them together, I will get BE. And when I take ED and CE and put them together, I will get DC. And then finally, since congruent chords cut congruent arcs, if arc BE and arc DC are congruent, then segment BE and segment DC are congruent as well. Okay. Number 4 doesn't have enough information to do anything with it right now. So what we're going to do is we're going to add in some lines, some auxiliary lines. In a circle, remember that the only lines you should really add in, at least at first, are radii. So I'm going to add in a couple of radii. I'm going to add in radius AD, and I'm going to add in radius AE. I still don't have two triangles, but if I do this, then they're connected. This should look a lot like the proof we did in lesson 6 in the homework when we did number 3. They're very similar because what we have is two tangents. So in that one, we used what we were given to first talk about how if we have a tangent meeting a radius at the point of tangency, it has to be perpendicular. And we're going to do the same thing here. So first off, we have circle A and tangents CD and CE given. And when I drew my radii in, I could say that therefore each of those tangents, CD for example, would be perpendicular to the radius that meets it. So CD would be perpendicular to AD and CE would be perpendicular to AE. And then like every time we've ever done perpendicular lines, they form congruent right angles. And so angle D and angle E would be equal and equal to 90. I can put a 1 and a 2 in there if I want to, or I can leave them as angle D and E. Okay, then I also can talk about how those two radii that I just drew in there are going to be congruent to one another. So AD would be congruent to AE. And then that final line that I drew in AC can be reflexive, just like we did in class. So AC would be congruent to AC. Okay, now if you look, I have angle side side, that's a problem, but wait, they're right triangles. So let me adjust this and make it an HL proof. So remember that if you have right triangles, they have to have right angles. Since I have right angles, I know that my triangles are right triangles. So triangle DAC and triangle EAC have to be right triangles. And by putting that in there, I'm saying, okay, it's not an ASS proof, it's actually an HL proof. So my triangles are actually congruent to one another. And then by CPCTC, I can finally get the two segments I need, which would get me A is congruent to B. And what I've just proven is that if I have two tangents from the same point, they actually are congruent. And some of you were asking me in class, and that's true. All right, number 5 is the same proof, except for the last step, we would use X and Y instead of A and B for our CPCTC. All right, finally for number 6, we have our givens. Just like the others, when we have a tangent perpendicular to a radius at the point of tangency, it's going to make perpendicular lines. And perpendicular lines form congruent right angles. So I have my 90s in here, 1 and 2. I also have congruent radii and vertical angles. So I have angle, angle, side, and CPCTC. All right, I'll see you in class.